Okay, so let's get started. And today is a session for USACO Gold and Platinum info or information sessions. So here's agenda. Me, myself is Dr. Wei. I'm instructor for essential class for USACO Gold and Platinum. That's why we offer 30 minutes to talk about two things. Number one, the data structure and algorithm footprint behind USACO Gold and Platinum. So basically what footprint or area you had to prepare before you throw yourself into a lot of questions. The second part in terms of strategies. The strategy for you preparing server is going to be different than you preparing for Gold and Platinum in terms of time efficient way. In that regards, I would say most of the 30 minutes for today, it's mostly on my end because it's not very easy to cram into 30 minutes and covering majority of data structure and algorithm topics. So let's try it. One more thing is today's session is not just about marketing sessions. I really want to be more technical aspect included or oriented for today. So in that regards, let's get started. The first one is regarding if you review data structure and algorithm required from silver into gold or advanced into platinum, it's a step function change in two manners. Number one is it will include new data structures such as disjoint, set, tree, or more, right? That's the first part. The second part is built upon the data structure or algorithm you covered in silver, but into gold and platinum, there's literally more in depth or combined with other algorithms. So in that manners, talking about strategies, being prepared for silver or bronze, I guess one approach is you can just go ahead with the questions literally, and from the questions, and you try to bridge into, okay, I need to use a greedy algorithm to solving that, or I might need binary search stuff. It's okay. The reason is that there's not much or many algorithms under silver or under bronze. You can do that. But the strategy will not be that effective if you try to go to prepare gold or platinum, because there's literally a lot data structure and or algorithm, and also in-depth manner. So strategy-wise, for my delivery, the first step or phase one, so we have to dive in-depth data structure and algorithm related in an organized way. So making sure being solid with that part before you can move on to attack more questions. And on that end, you can better bridge yourself into such as justify which algorithm or data structure should be used. So that is a strategy I see most effectively from past years and past sessions. So which is, I'm not a big fan of such as other organizations gonna starting say, hey, you know what, today's chapter, I gave you 3 years ago questions, do it. Next session, I'm gonna explain it. And why explain it bridge into data structure or algorithm, which is not very comprehensive manner. So on my end, I want to go like this manner, comprehensive first, and then move on to talk about any specific questions. So that's the purpose of today's sessions. I want to going through or comb through most, and not necessarily all of them, but most of the points behind data structure and algorithm. In that manner, so let's just move on by talking the syllabus. And then I'm gonna expand. Let me go to next page. So like I said, this is 10 chapter syllabus where it will capture most of algorithm and data structure behind gold and platinum. What I plan to do for next maybe about 20-25 minutes. Of course, I'm going to leave you some time for Q&A. I want to expand each topic, and we may not do very much detail driven, but just expand it, you understand the driver, you understand why, you understand some basic use cases. And this 10 chapters is encaptured into the Gold and Platinum Essential class. So why don't we just spend a little time understand the scope, the expectations, our handshake over what is called essential, that is, like I said, being very solid, being comprehensive into the necessary data structure and algorithm, making sure that part is very, very solid. And then with applications or user cases, so you can be solid on that foundations, and a little bit more based upon it, you can branch out and associate to basic applications. That's a very important before you throw yourself, like I said, just into the USACO questions, and then just accumulate many questions, and then at the end, if there's a derivative over certain questions, you still kind of, wondering or not much very solid with exactly looking at the solution, why I'm thinking of that way to solving it. So that's really relies on the first of it being very solid with what we just mentioned, the data structure and algorithm. In that manners, so let's first expand the first chapters, which is a greedy algorithm. I'm just go copy this and expand it underneath. Greedy algorithm actually is consistent from bronze, silver, and more. So greedy algorithm, the reason of that is because greedy algorithm is straightforward and also fast. But the matter to better understand the use cases of a greedy algorithm, actually there's a questions at what situations or scenarios I should use a greedy algorithm and why, right? So anytime you're using greedy algorithm, you literally has to prove it. These questions is a greedy questions. So we really need to understand what is a greedy algorithm and versus dynamic programming. Right, since now we are all into code, I guess you already know what is dynamic programming. And greedy and dynamic programming is all algorithms that starting from a small user case or smaller problem. That is a consistently seen from greedy and dynamic programming. The differences between the two is that, first of all, overall, most questions can be solved by dynamic programming versus greedy algorithm. But literally just greedy algorithm can deliver better time complexity. As to the distinctions over the two is that if you're looking at the small piece of the small problem, for greedy algorithm, it literally doesn't care what is previous smaller problem you have solved, what optimum solution you got from previous smaller problem, because it doesn't matter. If you cut the problem into n piece, the I piece versus G piece has no dependency. If that is case, you go ahead with the greedy algorithm. But for dynamic programming, well, there's a strong dependency from last previous smaller problems, and based upon that, you build up. That is a key distinction between the two. And actually in the sessions, definitely we have a lot of representative use cases to differentiate these two algorithms. And like I said, important thing is justify whether that is greedy problems, and so on. You can decide as accordingly. And also sometimes you can take the hint from input variables. Actually, there's another level of strategies, hopefully I can cover today, that is with given input variables and scales, you should decide, you should actually define the allowed time complexity or space complexity for any algorithm you want to propose. But in general, for greedy algorithm associated with the dynamic programming. And for dynamic programming, actually, we have much more. I'm going to expand later on. So chapter talking about the 2 pointers sliding window. So binary search is really a very straightforward searching algorithm. So this part, I would just say it's more like into coding scale. So-called as 2 pointers, which is literally you maintain several pointers. And let me get this. you maintain the pointers, then and with its physical meanings, and you maintain that physical meanings throughout the traversal or your algorithms. So mostly for this part, we're gonna talk about the user cases such as simulate the stack and solving the user case such as sliding window. And also you understand the user cases by 2 pointers could be merge sort and quick sort and many more. Idea about this chapter 2 is be very solid into define the physical meaning of the pointers and design the rules on how to move the pointers. That's the point for chapter 2. Right, and then move on to chapter 3, stack queue, priority queue. Actually, these 3 are actually belong to the server. But remember, as I said, there's an overlapping footprint from server to code, but just literally more in depth. First of all, in terms of those data structure, the requirement is you need implement on your own. Like I said, for example, stack, you can implement the stack into what? Like 2 pointers. You can implement the queue like what? Circular array or many more options. So the idea is you need to implement on your own. 2 reasons. Number 1, of course, you understand the syntax and implement the syntax. Number 2, you design on your own the time cost for how to add the data, how to pull the data, and many other operations, and based upon the question context. So that's actually another point for Go distinct from server. That is, sometimes you need to design your own data structures so that you can have the best time complexity for certain algorithm, for certain operations based upon the question context. Because literally there's no any one data structure can be efficient for any user cases. So that's why that's a requirement also. Okay, and the second one is for a specific data structure, you need to understand the user cases much, understand the user case and understand the driver better. I just give you example, just save the time. For example, stack. What problem you can think of, it's a stack problem. So generally speaking is when you're trying to scan a given data structure or traverse data structure from left to right, if you have to track the left elements and you need a stack. I'll just give you example such as calculating the largest rectangle. For example, just use an example to make the points as what's supposed to be in depth. The question is also very common for Go level. That is, you have a histogram and tell me what is the largest rectangle in terms of area. Well, if you go to brute force, that's a super easy, right? Just starting from each column, you go left, you go right, and decide what is span of the rectangle by using the given height, right? So what is the time complexity? Easily that's going to be quadratic, right? And this is a typically stack problems. And if you use a stack problem, literally you can drop down the time complexity almost to linear. So understand the driver, understand the user cases, so they can better bridge into the certain algorithm or data structure efficiently. So that's chapter 3. Chapter 4, talking about the dynamic programming. So overall for dynamic programming, this is one type of problems could be very difficult. So generally speaking, we're gonna discuss the dynamic programming into 2 dimensions and 1 dimensions. So you can see the 1D dynamic programming and the 2D dynamic programming. Mostly you see more 1D dynamic programming. You know, several easy user cases such as figure out what is the longest ascending subarray, right? Or what is the longest ascending subsequence. That's typical user cases for 1D dynamic programming. Or common questions from USACO such as a knapsack. right? Or such as a make the corn or corn change problem. That's a fitting the 1D dynamic programming. And like I said, dynamic programming is built up from small cases and you build up. It's a very straightforward structure, but important step lies in the transfer functions. You have to define the transfer function well. If you make that step really efficient, I mean reasoning parts, actually dynamic programming, the coding wise is a very short, very brief. And then for 2D dynamic programming, this is like I said, is make a DP can be a little difficult. So we will also include a 2D DP and user cases. For example, you can imagine questions such as 2 words and find the longest common substring. Right? This is typically can be resolved by 2D dynamic programming. All right. And moving on, chapter 5, chapter 6, graph search algorithm. The reason we have 2 chapters is because there's quite literally a lot. Graph problem is also starting from server, right? So basically that's a one of focus on server. But into Go, there's a more. And all more applications, such as we're gonna talk shortest path algorithms. And generally speaking for server setup, very fundamentally, they're gonna starting with how you're gonna represent graph, right? That's a very basic part. And then BFS transversal and DFS transversal. So these 2 traversing methods are straightforward, but very important. And in terms of, you're gonna decide which one in terms of its time complexity, also in terms of, context of the questions. Which 2 are actually enabling your following algorithms, such as, detect if a graph has a cycle. For example, how do you do topology sorting in a directive graph? You can actually go ahead and implement, but you had to decide why. That would be important parts between BFS and DFS in terms of graph transversal. So there's quite a lot of interesting summaries and practices behind the lectures, right? And now, like graph search algorithm 2, this is more actually talking about the user cases. As I just mentioned, you can think about questions like this. Detect if a graph has a cycle. And also you had to also determine the user cases such as this graph is directed or non-directed, right? So what's the strategy and what difference in your coding if the graph is directed graph or if it is a non-directed graph in terms of BFS or DFS? So my requirement is you have to implement both practicing wise, so that you can be very proficient to using whichever as your judgment call in your context. And the second is, which is topology. How do you sorting in terms of topologies? Also, mostly this one is talking about the directed graph. And also you should be very sorted by using either BFS or DFS. So BFS or DFS, this is just literally a transversal method. And for DFS transversal, you could actually using iterative or recursive, both manner to implement the DFS, right? So like I said, so-called in-depth, we are not big fan of just throw questions and telling you, hey, this is DFS solution. And we don't want to follow. What our way is, we need to explain or understand what difference between the 2, what difference in terms of iterative or recursive to implement the DFS manner or transversal first, being sorted with those parts before we're talking about specific question or solution. So chapter 6 it is. In chapter 7, like I said, this is a applications for more user cases based on graph, which is the shortest path algorithm. Very interesting topic. So this one is the question is in the graph. Now I give you two nodes. So tell me, what is the shortest path? So-called shortest path is what is the total weight in terms of minimum total weight from node I to node J, right? So overall for this, there is a discussions as if the graph has an edge with the same weight, right? If the graph with edge with a different weight. So you need to understand the different user cases and your strategy accordingly. If the edge is the same weight, I mean, this is very easy situation. Just go ahead with the regular BFS, right? So this is like the checkboard gaming related, such as every time you just go ahead with one step. Guess what? That one step only costs 1 unit or something. So that's edge with the same width. So regular BFS can solve it efficiently. The problem is when edge is different weight, then you're gonna have a lot of algorithm discussed here. So mostly one thing I want to add in here is now we understand our strategies. Of course, for any algorithms, we are just go ahead with naive approach. Naive approach for this example, since the shortest path algorithm, naive approach is let's try to find all possible routes from node I to node J, right? So in order doing that, so we can go to DFS, right? And the problem with this one, this is NP hard. If you look at the time complexity from I to J, there's literally a lot, exponential level. So that's why moving on to here, let's go back to so-called Bell-Manford's algorithm. So the point we start from naive is that you need to understand the driver for whatever algorithm. It's literally due to two parts in terms of optimization. Number one, your existing naive approach has a redundancy. Number two, it has a repeated calculations. And that's why starting from naive, pinpoint that area so that you can benefit or appreciate this Bell-Manford's algorithm. Actually, this Bell-Manford algorithm is also brute force, but actually much better than all possible routes calculations. And then from Bell-Manford's algorithm and with a greedy, and you can deliver what? Dijkstra algorithm. Right? So this is called curve building up. You need to understand why. Okay. So and if any of you can also refresh your memory, what is type complexity for Bell-Manford's? Remember, what is that? That is a V times E. What is algorithm for Dijkstra algorithm? This one actually depending on what? Depending on your implementation for Dijkstra algorithm, right? If you are using binary min-hip, what is the time complexity? So that's the shortest path algorithm. Behind it, this is also our approach to attack this problem in general. Then chapter 8, disjoint set and segment tree. I mean, this is first part of differences from the server. That is literally, there's new stuff. First of all, regarding disjoint union set, disjoint set problem. Understanding the reason we want to have disjoint set, of course, there's the drivers, which is basically you can keep a group of elements, and that's the first part. The second part is you could have almost like a constant times in terms of operations, such as you're trying to add new elements or new sets, such as you want to merge the two sets together, right? And also a very common user case behind this disjoint set is trying to determine whether or not an element is in whichever set. For example, for a graph hasn't cycle, that problem, you can actually use this disjoint set to implement it as well. So regarding on that, we're going to discuss or expand the distance set, also including the optimization, such as for your fine algorithm, we have a path compression. And for your union part, we're going to discuss union by rank, mostly, and also by size, and understand why. And for segment trees, this is a data structure. That's what I'm saying. For silver and lower levels, this is mostly transversal. It's just on a node. But then for binary index trees, you are actually looking at the range. And also respond effectively for range queries. So then you're gonna come up with a binary index tree, all right? And also for binary trees, actually there's a lot of problems combining with the DFS. So here's, we also have a kind of summaries in terms of organized ways, talking about transversal, that's very basic, right? Pre, in, and post. And more, it's special for binary tree combined with the DFS problem. There's quite a lot. The reason is because the nice structure of binary trees, it's always following a repeating substructure. That's why it combined with the DFS really well. In terms of time matters, so you just need to understand there's quite a lot of problem being combined on the binary trees. And then chapter 10 also, I include the tree. I guess this is also, for some of you, this is a new data structure. Again, for any data structure, we need to understand two things, the time cost in terms of operations, in terms of add, in terms of delete, in terms of insert, in terms of more. The second is based upon that, you need to understand the use cases, right? So why we need a tree for solving what problems. But overall, this is just a tree and a search tree, to be honest, for this data structure. With that being said, you need to understand what is difference versus binary search trees. Since it's a search tree, why not using binary search trees? One of the differences for the tree is that it's a key for whichever you want to search is not associated on the node like a binary search trees. And for this TRIE data structure, it's associated on the edge. So that's one of the differences in terms of implementations. And in terms of use cases, you can think about a use cases such as design a dictionary. What is dictionary? It's starting with A, B, and C, and alphabetical level, right? And starting from A, you have AA, you have AB, you have AZ, more, right? So the nice thing about the tree is, especially when you have use cases or problems, have a lot of repeating, has a lot of repeating the, for example, the sub-array, or repeating the beginning parts, and then tree is definitely a good candidate for you to consider. And also for these parts, you also need to be very solid into hash map versus sorted array list, and versus a balanced binary search tree, all right? And then compare with a tree in terms of time cost, in terms of how it costs for adding data, for searching the data, for delete the data. And the point is not trying to deliver the detail, but the point that you take this as a measure on how exactly essential class should be delivered and what to be delivered. And the second part is, even though you prepare on your own, you should have such a sense and a strategy. So do please not dive into the questions. You still have a half year, making sure being solid with data structure and algorithm in depth manner, and before you throw yourself into that. And the ninth thing behind, the essential class, if you allow me to go up, is the topics being organized and also expanded in the right manner, as I show you quickly. So that pretty much a nice 30 minutes delivery, I guess. we understand the strategy, how to prepare gold. And first of all, I forget to congratulate people who secure silver. That's really something already. Now we want to position ourselves into a more successful positions for computer science generation approach. So we definitely want to using our time efficiently, especially I guess you into grade 10 or 11. So we really want to bear such a strategy, starting with a comprehensive, in-depth data structure and algorithm, review and practice, and being solid with applications before we're moving on, right? So in that matters, that is today's 30 minutes info for USACO Gold and Platinum. So the class is 10 sessions, total 15 hours. All right, any question? Okay, and I'm gonna leave my email address here. I guess if you have any technical driven or aspect questions, go ahead and we can discuss. And if you're interested into enrollment, and you can go ahead and contact the center staff. So I guess that's gonna be a good start. Yes.
I have a question on the lesson. So it's 15 hours, and then how about the practice hour? Do they get log into a platform to practice, and how long will they have to practice, and what kind of assistance do you offer?
For essential classes, we are not into that phase to practicing questions. The focus for essential is to understand in-depth data structure algorithm. So each student will have a coding pad where student need submit the code. I will review it, give the comment, and iteration start from there. So definitely there is you have to pass into user cases for given homeworks.
Oh, in each of the lesson on the 10 chapter, you have given homework. You have homework for them.
Oh yeah, of course.
Okay.
We have a homework, and each student will have a kind of Google Doc coding pad. So basically submit your code there, and test it. I would test it and give you comments, and student gonna go ahead and correct it until it's passing everything.
So it's not like a platform they can enter their code to get it corrected. You will do it manually for them.
Yeah.
Or they would already have tested their code or something. I mean, they right? I mean, because when they code it, they would have using some kind of coding program to do it, right?
Right. The reason is that it's a rather easy. I can find the platform for students, just go ahead and submit the code and then come back, tell me how many user cases passes or not. It's the point for essential is that I need to understand the students' reasoning on justify using which data structure and algorithm and whether or not using correctly. So it matters more for me to review students' code and making sure it can justify the right parts, theory parts, before literally testing the user cases on certain platform, right? That makes sense?
Yeah, thank you.
Thank you. That's good questions. I have a questions. How should we approach learning recursions? So recursion, that's overall, that is a bronze and a silver level concept to start with. So Alvin, I don't know your status, but we also have bronze and silver essential class also, which will covers, if you go back to looking at the table here, I didn't include in the bronze. So recursion is well in silver and bronze bracket. And so for people who are interested into the bronze and silvers, actually, I didn't include it for today's session for focus. So you can go ahead and check with the center stuff. We also have essential class for bronze and silver. All right. Any other question? All right. if no questions, so appreciate your time. And if you have any other questions offline, go ahead. You can come across. We can discuss in email. And if you want to know more about enrollment, and go ahead and contact your center staff. I wish you successful in your next chapter for USACO contest. Appreciate your time. Bye-bye.